This is the capacitor, and here I've got the resistor. This is the ground, and here I've plugged in the channel 1 of the scope, and here I will observe the channel 2 of the scope. All right, so what I wanted to show you, in practice how we can find the maximum current which is appear in our electronic circuits, in fact, which is consists the RNC component when the switch is closed or when it is closing. We know that from the lecture and from the classes also, that the first moment when the capacitor is empty, it is like the short circuit. Yeah. So, in fact, at the beginning, we've got the 5 volts with just the pure resistor. Yeah. So at the first moment, we will observe the current I, max current, which will be equal E over R. It means it is 5 volts over the resistances. Something is, whoa, I don't know what happened. Okay. I will just run again. Okay, now it's work. All right. Okay. The next thing, how we can find the current. Of course, we can find them not directly, but indirectly. How? Measuring the voltage drop on this resistor. Okay, and observing its value on the scope. You have to know that the scope has the 2 wires. Of course, one of them is negative, one of them is positive. This positive is named like the signal, and this negative, it is our ground. So, as you see,
Sir, I'm sorry, we still have people that are trying to join, but they have the please wait screen.
Okay. I have to click on the admit all, I think.
That is correct.
Okay, thank you for a minute. I don't know why, because previously I never will, and I've never used it.
They changed the default because people were coming in, like people from the outside, like they were guessing the links.
Okay.
That it still can be changed. It's just that the default is different now.
Okay, thank you.
Yeah.
Thanks, Wojciech. Okay, so as you see, observe. If you want to observe something on the scope, we have to plug in the one of the wire. It is the ground and our signal. If we will have the situation when the resistor will be first and the capacitor will be directly connected to our ground, it is problematic to plug in directly the scope to the resistor like that. Why? Because the scope has the ground here. However, this is not the ground of our electronic circuit. I think I have to maybe run again this webcam server, because I see some lags. Okay, now is better. Okay, so the problem is that this ground, which is connected with the scope, will have the different in potential than the ground which is coming from the voltage source. As you see, I use this analog discovery board, so every grounds are connected together. So I can do that in this form. That's why I changed the position of the components. That's why the first is capacitor, the second is the resistor. As you see. Why? Because in that way, I can directly, okay, I have to stop for a while. I have to stop for a while. I'm just wanted to run again. Okay, I got it. Okay, landscape, great. Okay, and the full screen. Okay, I've got it. And now, okay. So, do you see the board now?
Yes.
All right. So that's the reason, because in this case, the channel of the ground of the first scope channel is connected to the ground of our circuit. Great. So let's check it. How looks like the signal? We know that at the first moment, the current and the voltages on the resistor should look like that. Yeah, we'll have some peak at the first moment, and then the exponential function connected with the charging process of the capacitor. And here we've got this E max value. Yeah. Okay. So we expect that waveform. How to calculating this I max current? It is E over R. Okay. So we'll check it. Great. Let's do it. Okay. I'm coming back with my board. I have to plug in, as you see, the positive voltage supply, and this is the red, that is plus, and of course some ground. It is here. That's all. I think that I see some problems with this admit process, because when I do it, this webcam server is stopped. I don't know why. Okay. 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 Now it's working. Do you see some changes on the screen?
Yes, but slowly. But I think it's this. No, it's more choppy than usual.
Okay. We have to wait just the 1 minute. I have to run again this this webcam server. Okay.
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 Okay. That's better. Great. Okay. So we are coming back. So what I have to do, I have to just plug in the pin to the ground to discharge the capacitor. Okay. I'm just waiting for a while. Okay. And in the next step, I will just plug in this pin to the positive power supply. It is the same, like I will close the switch and we'll observe the voltage drop on the resistor. Okay, great. So now we can go to the waveform. Okay, so now I suppose that you see the waveform software screen, yeah?
Yes.
Yes.
Okay, thank you. So what I have to do, as you see, I choose the trigger level here at the level of 1 volt. What does it mean? If will appear some peak at the one moment, from this point, in fact, this is our 0 of seconds, and the screen will be, in fact, stopped on the scope. So that works. Okay, everything is correct. We've got the channel 1. It is connected. The time base, let's say it is half of a second. The range, it is 2 volts per diff. Okay, it's correct. We've okay. First of all, we have to power on the power supply. As you see, the positive supply, I choose the 5 volts. Okay, the negative is turned off because we don't use it, and every supply is on at this moment. So we've got the 5 volts. Okay, and now I will run the scope at this moment and close the switch. Okay. I think I changed the capacitor. So maybe the base. The base is too long. Okay. I have to do again. Okay. And now I turn off the switch. Okay, I got it. Look, the trigger is find the point when the value on the channel 1 input value was reached the 1 volts. Okay, and then all of the plot was frozen at this moment. So as you see, we've got the waveform that should which appears correctly according to the theory. Okay, so what is the maximum point here? That's the question. We will see. Sorry. Let's change the magnitude of to the 1 volts, and let's shift it to the minus half of volts. Okay, it's correct. So I'm using the cursor to check what is the maximum point value. Okay, it is here. It is, as you see, it's C1. It is 4 point. I have to read it. It is the max. It is 4.922 volts. Great. Okay, let's coming back to our circuit. Okay. So that's the Vmax. What is the resistances here? Okay, I have to just take some very simple multimeter. I have to take the resistor and I have to just finding it. Resistances. How many it is? Okay. Okay, I have to take it to my hands. Nine, 5, I think. And again. I think this is not correct. Okay. Yeah, 985. So 985 ohms, as you see. Okay, let's coming back with our resistor. Okay, we got it. So the maximum current should be Vmax over 985 ohms. So it is 4.922 over 985. It is equal. Okay. .922 over 985. As you see, this is the 4.996 10 to minus 3. It means it is the milliamperes. So it is almost 5 milliamps. Why? Because the power supply, it is 5 volts. 5 volts, and this resistor should be the 1 kilo ohms. However, as you know, the accuracy of the components has some value. It means if we wanted to buy the 1 kilo ohms of resistances, so it is not possible to reach, in fact, that value. Real resistances will be different, in fact. Yeah. So, however, in this case, it should be 1 kilo ohms. As you see, where's the differences here? Our resistor hasn't got the 1 kilo ohms. In real, it has the 985 ohms. Okay, so as you see, if you take a look at, and again, something was happened.
Excuse me?
Yes.
About that camera, because like we see it like at a very low frame rate.
I see. Yeah, I don't know why, because to this moment, everything was working excellent. I don't know what happened today.
I mean, like even before, we also saw it at a low frame rate, but it's even worse today. And I have a suggestion, maybe a solution. Maybe it would be
change the resolution. Yeah.
No. If you connected to the Zoom meeting from your phone and just shared the camera of the phone directly, because there is the Zoom app.
It is possible.
Android, yes.
In the Zoom.
Yes, and you can connect it to connect the phone to the meeting directly. Share the camera. There is a button to switch between the front and.
Okay. Because on the phone, I'm using the IP webcam.
Yeah, I see. Yeah,
okay.
But maybe that would be like better if it's connected directly.
Mm-hmm.
And
question is, what's about audio quality?
Yeah, it could still be from the computer. Still could still be connected to the meeting. It's just
because it is
okay.
choose at
and on the computer as the host. I think you can choose like an option to spotlight the video.
Okay.
So that it shows up as the main one, like in screen sharing.
I think here I need some plugin, in fact, to iPhone, iPad screen. This is iPhone. Sorry.
No. I mean, like install actually the Zoom app from the Play Store, if unless you don't want to, but
on the phone.
Yes, and then you could like share the camera
on the phone. At this moment, the Zoom was installed on my computer at this moment. I will check it something. Okay.
Mm-hmm.
I'm just switch to the waveform. I will check it. What happened when I will. I've got one idea. Sorry for a while. All right. Okay, the full screen. Okay, it's work. And now, okay. Okay, I see some lags. It is better now or not? A little bit.
It just stopped working. So, oh, okay, something happened. Yeah, that did not.
Okay, I will change the one thing more. Okay. 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 Here. This is okay. Right. Full screen. How it looks like. Okay. Please tell me now is better if we think about the lags.
I think it is.
All right.
Okay.
The quality is worse. That's right.
I mean, it's not really noticeable over Zoom.
Okay. However, it's working now. Yeah.
Yes.
Oh, great. So, as you see, in calculation, as you see, the maximum current should be the 5 volts over 1 kilo. So this is the 5 milliamps. The real measurements show us, or real circuits show us, that the results are a little bit different. As you see, why? Because we haven't the ideal components. In fact, we've got also the measurement errors. Also, we have to take it into account. Also, yeah, great. So as you see, that is the very simple way to see that, in fact, when we turn on our electronic circuit, which will consist the capacitors, at the first moment we're observing the peak current. As you see, I show you that, in fact, it works in real circuit. And again, what I wanted to show you in the next thing, the last time we talked about on the lecture also and on the classes, that we'll have some phase shift between the sine waveforms when we have the inductor, when we have the capacitor. Yeah, that's right. I think yes. So what I wanted to show you in real that this phase shift, it is true. How we can make it? Very simple. I have to turn off the DC voltage source, and here I wanted to plug in the sine waveform. So I have to use the waveform generator. And the waveform generator on the channel first, it is this yellow wire. And of course, I have to plug in the ground. Okay. So at this moment, my switch is permanently closed at this moment. So the wire is connected to this generator. We'll observe on the second channel on the scope what will happen on the input. And here we'll have the capacitor and the resistor. And as you see, the channel first of the scope observing what will happen on the resistor. Okay. So let's switch to the let's switch to our waveform software. We have to turn off the power supply. We don't need it at this moment. We've got the waveform generator. Okay, so if we wanted to run it, we have to choose the frequency, the shape. It should be the sine, for example. As you see, we've got a lot of possibility waveforms for generating. Let's choose the magnitude to 5 volts, and that's all. Let's run it. Okay, now we run the sine waveform. Let's go to the scope. As you see on the channel first, we see some signal. Of course, the time base is too long. As you see, there was the 1 kilohertz frequency. So as you see, the period, it is 1 milliseconds. So to see something, we have to decrease the time base of the scope. Let's choose the 10 milliseconds, so we'll be able to observe the 10 of periods. Maybe yes or not. Is 1 milliseconds? Per diff. Okay, per diff. Okay, great. So as you see, we've got it. The 1 diff, it is in fact 1 full period. Let's turn off the offset. Okay, so on the channel first, we've got the sine waveform. Let's turn off it for a while. And this is the channel 2. Channel 2, as you remember, it is the input voltage waveform. This is it. All right. So let's turn on the BOF. I will just change the okay, let's say it is correct. Now we will see what I'm observing at this moment. The blue one, it is the input voltage waveform. The yellow one, it is the voltage across the resistor. So as you see, we don't observe any phase shift between the input voltage and the voltage drop on the resistor. Why? We know that there's no phase shift on the resistances. So it is true. If we're starting from this point, as you see, the sine waveform, the input waveform has the 0 degrees. Here it is 90. It is here we've got the 180 and so on to the 2 pi value. As you see, these two signals are in phase. The yellow one has 90 degrees when the input voltage has 90 degrees. There's no phase shifting here. Okay, so now let's coming back to our circuit and let's observe the voltage drop across the capacitor. You know, this capacitor is very huge. It is 470 microfarads. It is nice capacitor. However, I don't know if we'll be able to observe, in fact, the voltage drop in very good quality. It depends on the sensitivity of this scope. We'll see. Okay, so now what I wanted to do, I wanted to observe on the channel first the voltage drop on the capacitor. However, you know that I can take this pin and plug in here directly because the one of them, this one, it is our ground. So what I have to do, I have to just replace these two components. Yeah, I have to put it here, the resistor, here the capacitor, and then I will be able to observe the voltage drop across this capacitor. Okay, so let's take it off the resistor, and I have to put it here, the capacitor. Okay, I got it. And now I have to just plug in the resistor in the place where was the resistor previously. Here and here. Okay, I see. I think that I have it. Great, I have it. Right. So let's coming back to the waveforms. I've got it. Okay, as you see, the yellow waveform, the amplitude of the yellow waveform was dramatically decreased here. So it means that according to the input voltage, which has the magnitude of 5 volts, I think, it is very, very low. The most the voltage drop is observing on the resistor, not on the capacitor. However, let's increase the range. Maybe we'll see something. All right. 1 volt. Okay, 10 millivolts per. Something is okay. Okay, I'm changed to the auto. Okay, I got it. Okay. 20 milli. Okay. 2 milli. Yeah, I see something. Okay. As you see, this voltage drop on the capacitor is very low according to the resistor. So we'll have to change the resistances, and then we'll be able to get the voltage drop around, for example, 50 per 50 on the resistor and the capacitor. However, look what we've got. Let's stop it. Here we will see the resolution of our input AC/DC converters, not AC/DC, but analog to digital converter, which is on the input of the channel of the scope. Look what happened with the phase shift. The blue one, it is the input voltage. The yellow, it is the voltage drop on the capacitor. Look, when we have the 90 degrees, the phase, the input voltage, will have the zero angle, zero phase for the capacitor. As you see, it is true that the voltage or the phase shift between the input voltage and the voltage across the capacitor is shifted by 90 degrees. Yeah. What is the value of this shift? As you see, the same point, the 90 degrees of the input voltage, 90 degrees on the voltage across the capacitor are shifted by 90 degrees. Yeah, it is true. It is 90 degrees, but to the right. What does it mean? It means mathematically, the phase shift has the negative sign, so it is minus 90 degrees. At this moment, with this type of the analog discovery board, I can show you at this moment, at the same moment, what is the voltage drop on this resistor and the capacitor. However, indirectly, we know what is the angle, or what is the phase, what is the waveform observing on the resistor, because it is the same like the input voltage. All right. So this blue waveform, it is the same. Of course, the magnitude is different, but it is the shape or the phase. It is the same like for the resistances. Okay. So if it is the same waveform like for the resistances, so it is resistor. So that will be looks like the current waveform on the resistor. because this is the series connection between the resistor and capacitor, it will be the current also for the capacitor too. So this blue one, in fact, it is the current which is passing through by the capacitor. So as you see, we will see that this is the phase shift, in fact, between the voltage, it is the yellow sine waveform, and the current, it is the blue one. At the phase shift, it is 90 degrees. Okay, right. So as you see, that looks like in real. All right, so that was a little bit. We have some practice at this moment. So let's coming back to the classes. Let's make some properties or examples. Examples. And what else? So let's stop it. Okay. And let's switch to the camera. All right. Great. So can we start the first example?
Sure.
Okay. So I didn't send you the examples because I think it is not good idea, because in fact we make it in real. So please note it with me, the examples. Okay. So the first example, it is okay. It is like that. We have to find the load impedance ZL for maximum power transfer. Okay, and our circuit looks like that. We've got the load impedance here. Here we've got the current source with 2 amperes with angle 0 degrees. We've got some resistor, we've got some capacitor, we've got some coil. XL, it is 2 ohms. XC, it is 1 ohms. And here we've got some voltage source with 12 volts with 0 angle. Right. So we have to find the impedance value to get the maximum power transfer to it. Okay, we have to imagine, we have to remember what from the lecture, what is the maximum power transfer theorem. If you have impedance which is connected to our electronic circuits, which is represented by the equivalent Thevenin model, the maximum power transfer theorem tells us that real part of the load impedance should be the same like the real part of the Thevenin equivalent impedance. That's the first condition. And the second is that the phi angle for the load should have the opposite sign of the phi angle for the impedance of Thevenin equivalent impedance. Okay, and how we can write it in fact this moment. So if we have the ZL in the form like the RL, for example, plus minus JX L, load, it means load. And we've got the Thevenin equivalent impedance, which consists of the real part of the Thevenin resistances. As you see, the imaginary part of these two impedances should have the same values, however, the signs should be opposite. The real part should be the same. Okay, that's the differences. You have to take a look. You have to remember that the angle, but the signs should be in opposite, which means that the phase shifts are in opposite too. Okay, let's do it. Great. So as you see, at the moment we have to find the equivalent model for our electronic circuits according to the load impedance terminals A and B. So the terminals here, it is A and B in these points. So we have to take it off. We have to take off the impedance, and according to the typical Thevenin theorem, we have to find the Thevenin impedance across the A and B point. All right. So this resistor, it is 2 ohms. I forgot it. It is 2 ohms. Okay. So we've got the resistor here. We've got the capacitor. We've got the coil. Do you remember what we have to do with this, with the sources, when we wanted to find the equivalent Thevenin impedance or resistance?
Shorted.
Sorry?
Shorted.
Which one?
Voltage should be shorted.
Yes.
Current source should be open.
Yeah, because the current should has the 0 amperes. Yeah, should be 0 amperes of the current and the 0 voltage. Okay. However, we have to know what type of voltage we've got here, voltage source and the current source. What type of the sources we've got in this example? No DC. As you see, look, 12 volts with angle 0 degrees. It means that this is the RMS value of the sine waveform, which is shifted by 0 degrees. Here it is 2 amperes of the RMS value for the sine waveform with also phase shift equals 0. This is not a DC sources. Okay. Do you remember something about the dependent and independent sources? So in this case,
looks like
yeah, in
looks
this
like we do
case,
not.
we've got the independent sources. Of course, the sources are DCs, are AC sources. Yeah, we've got here. However, they are the independent sources. So the independent sources can be replaced by the short circuit and the open circuit, yeah, for the voltage and the current respectively. However, we cannot change the independent sources by the short or open circuit. Dependent sources should stay in our electronic circuit when we calculating the total impedance or total resistances. Yeah, as I remember, we made some example with it, yeah, or about it, where we have the dependent source, and in such way, in such a situation, we have to use this ohmmeter method. It means we have to plug in to our A and B terminals the EG source, and we have to find the current, EG input current, and then EG over IG current, it is in fact the impedance. Yeah. So in this case, we've got the independent sources, so we can replace it by the short or open circuit. And in fact, we've got the current source, so we just replace it by the open circuit, and the voltage source, we replace it by the short circuit. So how it looks like our circuit at this moment? A and B, it is connected in that way. The B is connected to the L. Okay, we've got it. The L, it is connected with the capacitor. However, in parallel, we see that the resistor is connected to the capacitor in parallel. And this point is going to the A. So as you see, we've got the total impedance or the equivalent Thevenin circuit. It is the series connection between the XL plus the parallel connection of the two components, R with XC. Okay. How many it is? Okay, let's change the numbers to the rectangular form. The resistor, it is 2 ohms, so the resistances, it is just 2 ohms. XC, it is the 1 ohms. However, this is the capacitor, so we've got the minus J1. Yeah, we've got the reactances for the inductor. It is 2 ohms. However, this is the inductor, so this is the plus J. It is shifted by plus 90 degrees, so it is the plus, so J, and J2 ohms. Right. So it is equal. XL, it is J2 plus. And here we've got the parallel connection between R and XC. So let's just substitute the values. The R, it is just the 2 times XC. XC, it is minus J over the sum of the R and XC. So the R, it is 2 plus minus J. Okay, we've got it. We've got it. So it is equal J2 plus minus J2 over 2 minus J. Okay, so at this moment, what we can do, because these numbers are so easy, we don't have to make the conversion to polar form due to this dividing process here. Why? We can make it in the rectangular form. How? Because in denominator we've got the complex number 2 minus j. So as you remember from the algebra, we have to multiply the numerator and denominator by the conjugate number, which is observing or which is on the denominator. The complex number, the conjugate number, it is the same number with the opposite sign before the imaginary part of the number. So we have to multiply it by 2 plus j over 2 plus jf. As you see, in fact, it is the numbers are the same. So the result should be the same because we can reduce it and nothing will happen. Okay, so it is j2 plus. Now we have to multiply the minus j2 by 2 plus j. So the first component is minus 2j times 2. It is the minus j4. Here we've got the minus j2 times plus j. So the j times j, it is j squared. So j squared is minus 1. So j squared is minus 1. However, we've got a minus here. So we've got the minus, it is plus, because j squared is minus 1, 2. Okay, over here. Here we can make the multiplication by the any components, which is here. However, we can use some mathematical expression for that situation. How many it is? It is because the numbers are the same, the changes with the signs. So this is in fact the a. This is a minus b, a plus jb. So we've got the same number. So it is the a squared. That's right. Yeah, minus b squared. Okay, so a squared, it is the 4 minus j squared. J squared, it is how many? It is j squared is minus 1. So minus gave us the plus. So we got that number. And this is equal j2 plus 2 minus j4 over 5. Okay. So, okay, so the total impedance here will be equal j2 plus 2 over 5 minus j4 over 5. So this is equal how many? Okay, it is 2 over 5. It is the real part of the number. It is 0.4. Yeah, that's right. This is the minus j4 over 5. It is 0.8. This is minus 0.8. This is j2. So we have to minus j 0.8 plus j 1.2. So that's the total impedance, which is here. So we know to get the maximum power transfer, the load impedance should have the same real part of the Z Thevenin impedance, but opposite phase shift here, which means the same imaginary part of the numbers with opposite signs. So in other way, we can say that the load impedance to get the maximum power transfer should be equal the conjugate of the total impedance. Total Thevenin impedance. Right. So the load impedance to get the maximum power transfer should be equal 0.54, the real part remained the same, minus J1.2. That's all. Then in our electronic circuits, we will get the maximum power transfer to the load. Okay, great. Okay, that's the first example. What about the next one, maybe? Because this example was rather simple. The next one. In the next example, something was happened. What happened? Okay, now it's good. In the next example, we have to find the load impedance to get maximum power transfer. And we have to find the maximum power. We have to find them. How it looks like the circuit. It is E with 0 degrees volts. We've got the resistor with 6 ohms value, the capacitor, which has the 8 ohms. We've got the inductor with the XL equal also 8 ohms. And here it is our load impedance. So we know what we have to do. One thing here, if we're coming back to the example which was previously, and when we have the equivalent Thevenin circuit and we plug in this load impedance, I told you that to get maximum power transfer, the ZL should be the same like the conjugate of ZTH. What is the total impedance observing from the voltage source point of view? Z total here, as you remember from the lecture, it is equal 2 times R, where R it is the real part of these numbers. It is simple because when you have the maximum power transfer, here we've got the ZTH plus, for example, JX, and here we've got the RL minus JX. So because these two components are connected in series, so we have to summing up these two numbers. So as you see, the X value, it is the same like the X here, however, with the opposite sign. So in fact, the plus JX plus minus, so minus JX is reduced. So as you see, if we're summing up the total impedance here, we'll have the ZTH plus ZL, only that. And because the ZTH should be the same like ZL, so in fact, it is 2R. What is the maximum power here? How we can calculate it? Calculating the Pmax, it is the same like the what? ETH times the current, total current, input current. Okay. However, we know what is the total impedance, so we can use the example or the expression for the power like the I squared R. Yeah. Okay. So it is the I squared R, where R it is the total impedance here. So let's write it maybe in that form. However, no, sorry. It is not the total. It is the resistances observed on the RZL. So it is times R. And again, sorry, I squared R. Okay, what is the I value here? The input current. It is the ETH over Z total. Yeah. Over Z total times R. Okay, so it is the ETH squared over Z total. I said that this is 2R. So the square it is 4R squared times R. So R is reduced with the square, so we've got the ETH squared over 4R. That's the maximum power observed to the observing on the load impedances. Okay, so let's make it. So that's the term. Okay, and we have to just calculate it. First of all, we have to replace this electronic circuit by the Thevenin theorem according to the A and B point. So we have to take it off. The impedance should be taken off, and according to the open A and B points, we've got the coil, we've got the capacitor, we've got the resistor, and as you see, we've got the voltage source, which is independent voltage source, so we have to replace it by the short circuit. Okay, so the question is, what is the Thevenin equivalent impedance? Okay, this is the 6 ohms, this is the 8, this is the 8. So ZTH, it is the parallel connection between the XL and these two components which are connected in series. Okay. All right. So this is equal XL. XL, it is the inductive reactances. This is 8 ohms, but it's inductive, so it is plus J. So this is the J8 parallel with the resistor. It is 6 plus XC. XC, it is 8 ohms, but this is the capacitor, so it is the minus J8 ohms. Okay, so this is equal. We have to just multiply two numbers in parallel connections. So we've got the J8 times 6 minus J8 over the sum of these two impedances, J8 plus 6 minus J8. Okay, so this is equal. If we multiply these two numbers, the complex number J8, we'll have J8 times 6, it is J48. Here we've got the J8 times minus J8, this is this 64. However, it is the minus 64 times J squared. J squared is minus 1, so minus gave us the plus. Okay, over J8 minus J8, it is 0. And we will have just the 6 here. So as you see, we've got the 64 over 6 plus J48 over 6. Okay. So this is our number. This is the total impedance here. So the question is what is our of course, this number can be reduced. Okay, this is the 32/3. Yeah, no, we can reduce more. Okay, plus J8. Okay, that's the total impedance. So what is our load impedance to get the maximum power transfer? It is the conjugate for the ZTH. So it is 32/3 minus J8. That's the total impedance. That's the load impedance. Load impedance should be like that to get the maximum power transfer to it. Great. What else? We have to find the Pmax, the maximum power observing on the impedance, where we have the maximum power transfer term is working here. Okay, so we'll need the ETH. Okay, how to find the ETH? We know it using the Thevenin theorem. So we have to coming back to our circuit. A and B point are still open. Okay, and we're coming back with the sources. Here we've got only one. It is the E, equal 9 volts with angle 0 degrees. Okay, so what is the Thevenin voltage value? It is the voltage across open A and B point. Yes, so this is it. As you see, in fact, this is the ETH. It is the same like the voltage drop on the coil. Yes, so I think if we consider these two components like the impedances, of course, we can use here the voltage divider rule to find the ETH. This is the voltage drop on the XL. Okay, so ETH will be equal the input voltage E according to the voltage divider rule. It is the input voltage times. Okay, in nominator we have to put the impedance where we observe the ETH. It is the XL over the sum of the whole impedances in our voltage divider circuit. So this is the R plus XC plus XL. Okay, so it is equal. Okay, so what is the E? E, it is the 9 volts with angle 0 degrees times XL. XL, it is the 8 ohms. However, in the polar form, this is the coil. So the phase shift is positive. It is 90 degrees plus 90 degrees. It means it is the 8 ohms with angle 90 degrees. Okay, in the rectangular form, it is the same like the plus J8. Yeah, this is the same. Over the sum of the whole resistances. Oh, sorry. How many it is? The R, it is the 6. The capacitor, it is 8 ohms. However, this is the capacitor, it is minus J8. Plus the inductor, it is the 8 ohms. Also, it is the plus J8. So as you see, the J's minus J plus minus J8 plus J8, it is 0. So we'll have what? And 9 times 8, it is the 72 volts, sorry, 72 with angle 0 plus 90, it is 90, over the 6. 6, it is the real number. So this is the 6 with angle 0 degrees. So this is equal 72 over 6, it is the 12 with angle 90 degrees, because we have to divide the two numbers, 90 degrees minus 0. So it is 90 degrees. So that's the ETH value. All right, we've got it. So the question is, what is the power, maximum power? The maximum power, it is equal ETH squared over 4R. Okay, how many it is? ETH squared, what does it mean? What is the number here? I mean, I mean, what is it? This is the RMS value or the maximum value? This is the polar form of the number. Do you remember?
RMS?
Yeah, this is the RMS. This is the RMS. So here, if you wanted to find the power, what is this? This is the real power. Yeah, this is the P. So the real power operates on the RMS values. Yeah? This is not the reactive power. This is the real power. So the ETH, it is the RMS value of it. It is 12. So this is 12 squared over 4 times the R. R, it is the what? This is the resistances for the load impedance when we have the power transfer term. So it is, this is it. This is the R. So times 32 over 3. So it is equal, it is the 12 squared, it is 144 over 4 times 32, it is 128 over 3. So the 3 is going
sorry,
up.
can you move paper higher?
Oh, sorry.
Thank
So the 3 is going up. So we've got the, how many? Let's check it. Times 3 over 128. So this is equal 3.375 watts. 3.37 or 38 watts. That's the power which is delivered, the real power, which is delivered to the load. And this power is maximal, because it is for the load impedance, which is in fact the conjugate to the Thevenin impedance here. Great.
So
Yeah.
if we would put resistor as load,
Only.
This would be power dissipated on that resistor.
Yeah, however, the power will be slower because the problem is this, the apparent power. Look, the problem is that to get the maximum power transfer, we make the situation that the QL, Q powers, in fact, this is the L and C. The Q powers has the same values of the Z total and the load. That's right? So we have to get the situation where there's two numbers will be going, will have the same value but opposite. Then it is 0. The P, it is the same like the S, in fact, yeah?
Okay.
Okay, thank you. Great. So we've got the two examples on connected with the maximum power transfer. So what you have to remember? You have to remember that the maximum power transfer we are calculating for the equivalent Thevenin model of our circuit. So we have to know it. What is the Thevenin theorem? We have to know that the ZL, it should be the conjugate of the ZTH, okay? And then we've got the maximum power transfer to the load impedance. And you have to remember how to calculating ZTH using the Thevenin methods, and how to calculating the ETH based on the same theorem, and how to finding the maximum power. Okay. Great. So I prepare another example, and this example is like that. We will have to find the average power delivered. Delivered to the resistor. Okay, the scheme is very simple. We've got the current source, which is connected to the resistor, which has the 4 ohms. Yeah. However, the current function looks like that. That is the seconds. This is the time axis with the seconds unit, and the current function looks like that. Okay. All right. So please tell me, if you wanted to calculating the average power, what is the average power? It is the P, yeah, power. So this is the average power, the P. How we can find them if we have the current and the resistor? What equation we can use for the power? So, Jakub, do you remember?
I don't know. Average?
Okay. The power in general, it is the what? V times I. Yeah?
Shouldn't we use here cosine?
Sorry?
Shouldn't we use here cosine?
No, we don't have to.
Okay.
Look, this is the V times I, yeah? That's right. What is the V according to the Ohm law? I times R, yeah? That's right. So it is the same like I squared R. Yeah? Of course, we can use the expression where we have the power factor here. However, you know that the power factor for the real resistor is equal how many? For the pure resistor. 1, of course. So the cosine, so in fact, the cosine phi, it is 1. So we've got just the V times I. That's right? Yeah.
Yeah, yes, because there's 0 degrees.
Of course, yeah. So as you see, we can use that formula according to the Ohm law, I squared R. Yeah, we've got the R, but the question is what the current should be put it here. I mean, what the value of the current, I mean, not the value, but what type of the current should be put it here. Please take a look at what we talked about previously for the previous example, where we have the 88 and we're calculating the power, average power. What the value should be put here by the current? It should be the what? Maximum current value or the RMS?
I think RMS.
Of course, yes. It should be the RMS. It should be the RMS current. So now you know why I put it here the waveform of the current in time domain. Why? Because we have to find from this waveform its RMS value. That's right? Okay, so how to calculating the RMS? Maybe you remember from the lecture, maybe not. We have to calculating the RMS value from the one period. Yeah. So first we have to take a look at our waveform, and we have to find where's the one period. So if you take a look at to this example, could you tell me what is the time of the period in this case? So period means this is the time where these waveforms are repeated. Yeah.
6 seconds.
6. Okay. Do you have any ideas? No. Of course, you have right. This is the 6 seconds. This is the one period. Yeah, because the another one, it is the same as the first one, yeah? And is during the next six seconds. All right, so maybe you remember the RMS value is calculating for the one period of time. What is the general formula for the RMS? If we have in this case, if you have some units, we wanted to find its RMS value. The general formula, it is like that. The RMS, root mean squared, yeah? It is the square root from the area. The area, it is integral from 0 to t, so for the one period, calculating from the unit function in time domain over the t, over the period. That's the general formula for the RMS value. Okay, so in this case, we have to find the RMS for the current. So the current RMS value, it is calculating from that formula. Here we have the squared here. I forgot it. It's unit squared. So it is the I squared function over t. So we have to find this value, the RMS value, from making the calculation based on such expression. All right. So first of all, let's finding the value of this integral. Okay. All right. Look, how many functions, if in fact, we've got during the one period of time? In fact, we've got the 3 functions, yeah? However, 2. One, it is just the simple function, which is equal to, yeah, during the time of from 0 to 2 seconds. The next function, in fact, this is the same. This is just the simple function equal 4, yeah, from the 2 to 4 seconds. And again, from 4 to 6 seconds, we've got the same function equal to, yeah, in this period of time. So as you see, full period consists of the 3 functions. So let's write it. The first one, it is the integral. So we have to find, in fact, the area under this function, but from the square of this function. Okay, so from 0 to 2 seconds, we've got the function, current function equal just 2 squared dt plus from 2 to 4 seconds, we've got another function, different function, equal 4 squared dt plus from 4 to 6 seconds, we've got again function equal to squared dt. Look, what's the differences here? Look, from 4 to 6, in fact, we've got the 2 seconds, like here. So, in fact, these 2 functions, or maybe the functions, the results of these 2 integrals will be the same. So we can solve these examples separately, or we can find that these 2 expressions are the same as the results. So we can calculate it in that form. It is 2 integrals from the first function plus the second one. That's all. Yeah. Okay. Okay, so this is equal to what is the integral from this function? The constant, it is 2 squared, yeah? So this is 4. 4 can be going before the integral. What is the integral from dt? Hello? The question is, what is the integral from dt? Do you remember? Okay. What is the integral from the x?
T, or
Sorry, Wojciech?
is it just t plus c?
Of course, however, we have the integrals with the border, so we don't put the c, yeah? So it is t, that's right. It is t with from the 0 to 2. That's right?
Yes.
All right, plus, here we've got the 4 squared, so it is 16 dt. 16, it is the constant value, is going before the integral, so it is the 16. And again, we've got the integral from dt, so this is the t from 2 to 4. And this is equal, this is the 2 times 4, it is 8. And we have to substitute by the t. 2 minus 0 plus 16, 4 minus 2. And this is equal 8 times 2, it is 16 plus, how many it is? It is 2. 2 times 16, it is 48. This is the 48. So we've got it. We found the expression for the integral from 0 to t from our squared function et. We've got it. So the RMS, it is square root from the this integral, so it is 48 over, let's coming back to it, over dt, over dt. At t, it is 6. T, it is 6 seconds. So this is square root from 8 amperes. Of course, if we wanted to calculating it using the decimal format, it is the 2.828 amperes around. Okay, that's the RMS current. So let's coming back and find the power. Power, it is equal I squared, RMS, of course, times R. So it is equal, you can see that, we've got the square root from 8, and this is, we have to power it by 2. So it is squared by 8 powered by 2 times R. R, it is 4 ohms. So this is equal just 8 times 4. So this is 32 watts. This is 32 watts. That will be the power dissipated on this resistor if the current function in time domain looks like that. Okay, so you can imagine that the current function is not looks like that. Maybe it could be like that. Can be? Can be. And this is our period. Where's the differences? The differences is here. We have to find the expression for this this function from 0 to, for example, 2 seconds. Yeah? If we have the 4 here. So we can find the expression. This is the linear function like the ax plus b. If it's starting with 0 here, so we'll have the b, it will be 0, and we have to just finding the slope of this function. Yeah, so we'll have the function like et, yeah, e times t, where the t it is the in seconds. Yeah. All right. So where will be the difference? Difference will be calculating the square root, calculating the integral from our function, which is looks like that, like et, where it is the constant value. So the differences will be like that. et dt. Yeah, it will be going before the integral, so we've got the t dt function. What is the t dt integral from t? Do you remember? So so as you see, the math is needed in electronics anytime.
Half of t squared.
Yeah, that's right. T squared. Yeah, that's right. So this is the t squared over 2 from 0 to 2. Yeah. So as you see, in that form, you will be able to find, in fact, the expression for the RMS current. I forgot about something. We have the I squared. So this function, it is squared. So in fact, it is the t squared. Okay, so how many it is? What is the integral from t squared dt?
One third of t to power of 3.
T power to 3 over
3.
Yeah, that's right. That's right. All right. Very good, Jakub. Okay.
Yeah,
yes.
When we have multimeters with this true RMS, the chip inside need to perform integration on the fly?
No,
different.
No, because any time where we observing the voltage drop on some components, or if the voltmeter is measuring the voltage is on some resistors, in fact, measure it on the resistances. So the natural is that on the resistor we're observing the RMS values at any time. So in fact, the voltmeter don't need some maths in this case. So naturally, if we have the sine waveform, for example, and we're measuring something by the voltmeters with true RMS, in fact, this is nature. In fact, it's natural, because on the resistor, anytime we've got the real power, the RMS values. The RMS values. The problem is when we have the voltmeters where we have be able to find the apparent power or the reactive power. Yeah, for that meters we'll have to make some calculations in fly to find them. Okay. All right, guys. So maybe the last example. Can we make it, or you have so tired at this moment? Do you want the last example? Yeah, Igor. Great. What about the last? What about rest of the students? Do you want or not?
Why not?
Why not? Okay. So we have. Please note. Please note the test of the next example. So the text is like that. We've got the industrial plant has got 10 kilowatts heating load, and 20 kilovolt amperes inductive load. Why? Because this plant consists of induction motors. Okay, and the heating power, or the heating element, are considered as not purely resistive, which means the power factor is equal 1, and induction motors have a power factor equal 0.7. Okay. So if the supply is 1 kilovolts at 60 hertz, we have to determine a capacitive element required to rise the power factor to 0.95. Please tell me if you will have it, if you will note it. Do you have it?
Yes.
Okay. So how it looks like our industrial plant? It looks like that. We've got the power supply, which is equal 1 kilovolts at 60 hertz. As you see, we've got some heating element or heating load where we observe the 10 kilowatts of power. What does it mean, the heating element? Heating element, it means that it should has the resistive character. That's why the heating elements are considered as the purely resistive, because this is the heating. We know that we have the pure resistor and we plug in the current source, then we'll observe some heating. Yeah. What is the power which is dissipated on this component? It is 10 kilowatts. Why? I told you that it is dissipated power. Look, this is not the volt amperes. This is the watts. The watts are connected with the average power, P. So in fact, this heating element should be the pure resistive character. So this is 10 kilowatts. And here we've got some motor plants or some induction motors, which has some power equal 20 kilovolt amperes. Volt amperes with the power factor equal 0.7. So what does it mean? The volt amperes, it is the apparent power. This is the apparent power S. Yeah, this is not the volt ampere R. It means the reactive power. It is 20 kilovolt amperes with 0.7 of the power factor. How it looks like? Sorry. How it looks like on the power triangle. It looks like that. We've got some pure resistive character. PR, yeah, which is equal 10 kilowatts. Okay. However, we've got also some power which is connected only with the motors. All right, so if it is 20 kilovolts volt amperes, so this is the apparent power with 0.7, so we have to find what is the reactive power here and what is the real power connected with the motors. Okay, so I'm just writing or plotting here the real power connected with the motors, and I have to put it here the reactive power here. Look, this is the motors, so it is the elements where we've got the inductions. Yeah, so the reactive power should going up here, and this is it will be the QL or the value, yeah, or QM, maybe QM for the motor. Yeah. All right, so the 20 kilovolt amperes, in fact, this is the apparent power S equal 20 kilo. Okay, great. What is this angle here? This is the phi m. This is the angle connected with the motors only. Great. So let's finding this the angle here connected with the motors and its real power and relative and reactive power. Okay. But from beginning, the S, the apparent power, it is the VI. Yeah, that's right. This is the RMS of V and RMS of I. We know that the P, the power, the average power, it is the equal. This is equal VI and cosine between this V and I phase shift. This cosine, it is the power factor. We know it. However, the P, it is the same like the S times cosine phi. Yeah? That's the relationship between the P and S. So, for induction motors, we've got what? SM, it is the VI, and this is given, it is equal 20 kilovolt amperes. We've got it. So what is the P? According to this formula, it is the SM times cosine phi, and this is our power factor. So it is equal 20 kilovolt amperes times 0.7. We've got it. Okay, how many it is? It is 14 kilowatts, because we are calculating the PM, the real average or real power. Okay, how we can find the QL, reactive power? Of course, we can use the some expression that's using the Pythagoras equations. We can find the QL, or QL. It is the same like VI sine phi angle. This is the same. So this is the SM times sine phi. So phi m, it is the m. All right, how many it is? Here we've got the m also, because we are considering the motors here. We have to get or find the phi m. Okay, how many it is? We know that the power factor, it means the cosine phi m, is equal 0.7. So the 0.7, it is equal cosine phi m. So the phi m, it is the what? The Arcus cosine from 0.7. So if you calculating it, we will find that it is the 45.6 degrees. We can check it. The cosine to minus 1 from 0.7. Yeah, this is 45 point. Okay, 5.7. This is around 6. Okay. So we've got it. So we've got the phi m. So the QL will be equal. SM, it is 20 kilovolt amperes times sine from 45.6 degrees. So this is equal 0.714, and this is equal 14.28 kilovolt ampere R. R means reactive. Okay, we've got it. So let's coming back to our power triangle. And this is 40.28 kilo. We've got it. So what the question is, because we've got the S, we've got the power triangle considering only the motors. However, we have also the heating element. So totally, our triangle for our plant is given by that triangle, where here we've got the S total. Okay, look at the if we're summing up the powers here, we have to adding to the average power connected to the motors. We have to adding also the power connected with the heating element. Okay, so as you see, that's why we have to build we can build the ST in that form. That's our triangle, power triangle for our plant, our industrial plant. Here, the real power, in fact, this is the then the P total, it is equal PM plus PR. So this is equal, the PM is how many? 14. The PM is 14. So it is 14 plus 10, it is 24 kilowatts. That's the PT. QM are not changed. Why? Because this element, the heating element, consists only the real power. Yeah, we can observing only the power dissipating on this element. So the pure active power is connected with the heating element, heating load. All right. So the ST. So let's find this ST. How many it is? ST can be calculated using this Pythagoras, for example, formula. It is the square root of the PT squared plus QM squared. Okay, so this is equal square root of 24K squared plus 14.28 squared kilo, of course, and this is equal around 27.93 kilovolt amperes. So the length of this vector, ST vector, is equal 27.93 kilo. All right. Okay, the question is, at this moment, for our plant, for our industrial plant, what is the power factor? This power factor is given here by this angle, phi t. Yeah? So if you wanted to find this power factor at this moment, we have to finding the phi t, the phi t. Phi t, it is equal like what? We can find it in different ways. Look, we can use the sine function. If we use the sine function, the sine phi t, it is the same like qm over st, okay? Or we can use the cosine function. For the cosine, it will be equal cosine phi t, it will be the pt over st, okay? So we have the two ways at this moment. Not the two, because we can use the tangent or cotangent function. However, it could be the sine Arcus sine function from the QM over the ST, or we can use the cosine function. So it will be the Arcus cosine from the PT over ST. So we can use this, for example, cosine function. So it will be the cosine to minus 1 from 24K over ST. It is 27.93K. So it will be equal around 30.75 degrees. That's the angle here. All right. So if we're coming back to our example, what we have to do, we have to determine the capacitive element which is required to raise the power factor of our plant, of course, to 0.95. How we can increase the power factor? If we've got the S total here, we've got the P total here. Okay, and this is our QM, the reactive power connected with the motors, and this is phi t. We have to reduce, rise the power factor, which is equal cosine phi t prime, should be equal 0.97. No, 97. How many? 95. So the question, how many, or what should be the phi t prime to get the 0.95? But first of all, this angle, let's calculating it. It will be easier. So the q t prime, it is equal arcus cosine from 0.95. So it is equal 18.90 degrees. So the new angle should be here, phi t prime. And as you see, for that angle, for 90.9, for 80.90 degrees of the phi t angle, we can get the power factor equal 0.95. How we can make it? We have to reduce the QM, the reactive power connected with the inductors. Inductors. So what we can do? We have to adding the extra some components which has the negative reactive power to the inductive load. What is it? It is the capacitive element. This is the capacitor, because then the capacitor, which will have some QC reactive power, if we summing up these two reactive powers, we will get the QM minus QC should give us QM prime. Yeah. Okay, so as you see, we have to adding the extra capacitor to our power plant or industrial plant. So we have to adding here the capacitor. The question is, what should be the capacitive here to get the power, the total power factor equal 0.95? First of all, we have to find the QC. We have to find the QC, the value of QC when we'll get the QM prime value. Okay, so first of all, we have to know how many it is the QM prime. This QM prime can be calculated from what? For example, tangent function. The phi t prime, it is the same like the tangent. Okay, tangent function from QM prime over PT. Yeah, it can be. Okay, so we have to use the arcus tangent from QM prime over PT. Okay. This is the, okay. This is the phi, sorry. This is the phi. No. Sorry. The phi t prime, it is given by the Arcus tangent from qm prime over pt. Okay. So from this from this formula, or we can, this is it. So we can write it in other form. The tangent from phi t prime, it is qm over pt. All right, and qm prime, and from this qm prime, it is the pt times tangent from phi t prime. All right, I've got it.
I'm sorry.
Yes.
Somebody lost connection and is waiting.
Oh, sorry. Thank you. Okay, so we've got the qm prime, the new qm prime. It is pt times tangent from phi t prime. Phi t prime should be a 18.90 degrees. Okay, so we can find this value. Qm prime, it is pt, it is 24 kilowatts times tangent from 18.90 degrees. So the qm prime, it is equal 24 kilowatts times tangent from this value, it is around 0.329. So the qm prime, it is around 7.9 kilovolt amperes reactive power. Okay, so we've got the qm prime. All right. If you have it, we can find how many should be the QC. Yeah. So it is very simple to finding, because the QC, it is the total QM minus QM prime. Okay. 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 Okay, maybe that will be better. So the QC is equal. QM, it was the 14.28 kilos minus QM prime, it is 7.9 kilos. So it is equal 6.38 kilovolt amperes reactive power. So we've got it. We've got the QC. So the question is how we can find the capacitance. Okay, let's coming back to the lecture when we talked about capacitance. Maybe you remember that the QC, the XC, it is equal how many in general? One over omega C. So the capacitive reactance is equal 1 over omega C. This is the same like the 1 over 2 pi F C. All right. So from this formula, the C is given by the equation looks like that: 2 pi f x c. You see, we've got the frequency. This is 60 hertz, and we have to find the xc. All right, how we can find them? We've got the QC. We've got the reactive power. Okay, so how many is the reactive power connected with the capacitor? Typically, it is the VI. Of course, we can using the Ohm law, we can represent it in that form. It is the I squared XC, yeah, or V squared over XC. Yeah. If you will have the resistor, we will have the I squared R over or V squared over R. For the capacitor, we've got the I squared XC. For the inductor, we'll have the I squared XL. Okay, the question is, what is the voltages on the capacitor in our case? This is the power plant supply power. This is the voltage equal 1 kilovolts at 60 hertz. This is the same voltage across the capacitor. So we can use that formula. QC, it is the same like V squared over XC. V, it is the same like, in our case, E. Great. So the XC, it is the E squared over QC. So this is equal. How many is E? This is 1 kilovolts squared over QC. QC is 6.38 kilovolt ampere R. Okay, so this is equal 1 kilo squared over 6.38 kilo. Kilos is reduced, so it is equal 156.74 ohms. That's the XC, capacitive reactances. Okay, so let's coming back to the to this formula for finding the C. The C will be equal 1 over 2 pi times 60 hertz times XC. XC, it is 156.74. And this is equal and this is equal 1 over the 2 pi 60 times and 66.74. Okay, it is equal, as you see, around, of course, 16.9 microfarads. That should be the capacitance, capacitance of the capacitor, almost 17 microfarads, to get in our plant the correction of the power factor to 0.95 value. What does it mean? In fact, we can say that our industrial plant will have, in such configuration, almost the pure resistive character. almost. If the question will be, please find the capacitive elements needed for raising the power factor to 1, oh, it is also possible to find them. Then our XC should be equal QM. Then QM minus QC, it is 0 of the reactive power. Then ST prime will be the same like the PT with angle 0. Angle 0 gave us the power factor to 1. So it is also possible to find the capacitance to get the correction of the power factor to 1. It is possible. All right, guys. So I think at this moment is enough. So after Easter, we'll starting with the next classes and the last lecture. I'm wondering about this test from the lecture. However, I know from some sources that making the tests by online, it is not a good idea, because the students are using at the same moment any other communicators. So even I will prepare some tests, and I will give you, for example, 30 seconds for the one question to choose the right answer, A, B, C, D, or not, or something like that. Then using the at the same moment, you can use the communicator, the other communicator, and you can in fact tell everything what answer you choose. Even I will give you the 30 seconds. So that's the true. I know because some people are made the tests or try to make this test by online, and we know that it looks like in that form, in fact. So at this moment, there's no any other way to make this test at the end of the semester, I think. I don't know what you think about it. And Julia, don't send me any answer from your point of view about the test. So if you will have another ideas, you can tell me about the possibilities to make this test online without the situation where you will contacting with yourself during the test. So please think about it. Please thinking about it, because we have a little more time, because the test can be should be in fact typically after Easter. So we have a little more time to think about it. If we will not find some solution, so I think there's no any way to waiting for the end of semester, and then we'll prepare the test from my side, from my part, and from Adam part, and then we'll make, if it will be needed, of course, the extra tests for the people who, for example, didn't pass some part, my part or Adam part test. All right. So I think please talk about it yourself, and if you will find some ideas, please, Julia, please write to me the email about your proposition of proposals. Okay. And what else? That's all. That's all, guys. So again, thank you very much that you will be with me at this moment and for watching. So please make the examples also from the book. What else? I will, as I told you last time, I will prepare some extra classes using this analog board to show you the frequency characteristic. Also, I think this online courses or course will be much more interesting for you, where we'll have some practical elements during this course. Okay, so thank you again. So for everybody, I wish you the very nice, beautiful Easters. I know that we have to stay at home, but I think Easter, so it could be also in that way. So thank you again. Do you have any question? Okay, if there's no any questions, thank you again. So we will see the after Easter on the classes. Yeah, on the classes, I think. Yes or not? Let's see. Or on maybe on the lecture. I will send you the email about it. Okay, thank you again. So see you. Bye. Goodbye.
Thank you. Goodbye.